Welcome to the QEF channel, where we present our road cycling research results in an informal way. In this first video, we will focus on the aerodynamic effects of two BOA dials on a road cycling shoe. We chose to study a high-end specialized shoe with two BOA dials, the S-Works torch model. This is a fairly typical configuration found in many cycling shoes currently in use. Cycling shoes can be considered bluff bodies. However, the upper part of a smooth cycling shoe, which is the main area exposed to airflow during the pedaling cycle, does not create significant turbulence. Therefore, from an aerodynamic perspective, the presence of two bumps, such as the dials on top of the shoe, might appear awkward. To evaluate the aerodynamic impact of the two dials on the shoe, wind tunnel testing does not provide satisfactory results. First, a mannequin should be used because testing with a real person, especially while cycling, introduces reproducibility problems, making it difficult to isolate differences in drag due to small details like the two BOA dials. A wind tunnel test with a mannequin. Initially wearing the shoes with the dials and then the same shoes without them would only provide total drag forces for the two configurations. The analysis possibilities in a wind tunnel are limited, except for the injection of smoke, which can offer some general information on air movement. As an alternative, computational fluid dynamics (CFD) offers equally precise results, and it provides detailed data on how air moves around the body, including parameters such as pressure, velocity, and vorticity. CFD allows for multiple simulations to understand how design changes can affect drag by delaying boundary layer separation and ultimately reducing wake formation. It also enables visualization of data through a variety of 2D and 3D plots and animations. For these reasons, we chose to conduct a CFD analysis using an open-source software called OpenFOAM, which is widely recognized in both the automotive and aerospace industries. The simulations included the shoe and the ankle to accurately replicate the interference that the dials can exert on nearby elements, including additional parts such as the whole leg, body, bicycle, or ground would not have significantly altered the simulation environment. However, it could have introduced extra elements that might amplify diffusion errors. The shoe was studied in a position parallel to the ground, which approximates the scenario when the crank reaches 110 degrees relative to the top dead center, that is the zero position in the pedaling cycle. Other possible inclination of the shoe while pedaling would not substantially change the exposure of the dials to the airflow. The imposed airflow in our study is due to a riding velocity of 50.4 km per hour, equivalent to 14 meters per second, and no external wind. While the situation would change in the presence of a lateral wind, we consider that the two shoes would exert counterbalancing effects. Lastly, our position is static and it doesn't account for the rotation of the shoe around the bottom bracket. At 100 RPM, the tangential velocity is 1.8 meters per second, which is much smaller than the air velocity. If included in the simulation, it would only have a minor influence. Every simulation software requires a digital model of the object being examined. To create this model, we chose to design the specialized shoe using Blender, a 3D computer graphics software. There are several reasons for this choice. A 3D scan of the shoe would have simply replicated it without discerning between critical components and those that could be smoothed out or omitted to improve the simulation results. We used Blender to design both the shoe with BOA dials and an identical one without them. Let's take a look at the results. This animation displays a top view of the vorticity. The shoe without BOA dials is shown at the top, while the shoe with BOA dials is shown at the bottom. Vortices are plotted using a color palette that reflects velocity magnitude. Red indicates the highest velocity, while blue represents near zero velocity. The first vortices form at the tip of the shoe and split as they move backwards. The rest of the top frontal part of the shoe without BOAs does not show signs of turbulence. In contrast, vortices appear behind each dial on the bottom shoe, propagating backwards towards the wake. So, comparing the two wakes of the two simulations, the difference from the shoe without dials displays in the top of the screen is evident. The ankle has a straight cut that alters the airflow, causing turbulence. However, this is a divergence from the real-world scenario due to the simulation setup. This is not relevant for our final considerations on the dials effect. In this new animation, we see the two tested shoes from a side view. We observe the same phenomena seen earlier from the top view. In particular, we highlight the turbulence generated as the airflow moves around the two BOA dials. The vortices from the front dial are deviated downwards by the air passing through the bottleneck created by the two dials. The vortices from the back dial move along the free stream direction. Let's take a moment to clarify a few aerodynamic concepts before continuing. First, according to Bernoulli's principle, pressure is proportional to the square of velocity. This rule applies to any fluid which is incompressible. It translates to high pressure when velocity is low and low pressure when velocity is high. However, Bernoulli's principle is valid only when there is no turbulence. Therefore, in the back, where you can see vortices, this law cannot be applied, and both pressure and velocity are simultaneously low. Second, the longer the air remains attached to the surface, the smaller the wake, the highly turbulent area behind an object. A way to detect where the flow separates from the surface is by observing where the velocity of the air abruptly decreases. Soon we will use these concepts. We will now introduce another method for visualizing vortices. In this first image of the shoe without dials, the slight turbulence in the front part is not significant and does not extend backward. The only exception is this small vortex we observed earlier in the animation, which originates from the shoe tip and splits on both sides. The simulation did not consider the cleat and pedal, which would obviously interrupt the flow. Nevertheless, it is interesting to notice how some vortices appear after the small step on the sole, which is sufficient to create a propagating turbulence. On the sides of the shoe, the separation of airflow generates the major part of the wake. The separation point occurs late on the left and right side surface, causing the wake to be narrow. We can conclude that even though the shoe is a bluff body, its frontal superior surfaces are quite aerodynamic. Looking at the ankle, a few considerations can be made. This area shows an early detachment of airflow, generating major vortices. The findings suggest that air attachment on the ankle sides can be improved with dedicated socks. This is not an easy task if the socks are intended for a range of velocities and different inclinations of the shank. Here is an LIC image plotted with a color palette reflecting the magnitude of the velocity, which can help understand the flow. Red indicates the highest velocity, while blue represents zero velocity. This technique generates texture patterns that reveal the flow direction. The result is similar to the surface oil flows that can be obtained in sophisticated wind tunnel testing. The red areas where velocity is high are followed by yellowish areas where air is still moving and, as explained earlier, will remain attached to the surface. On the ankle, however, after the red zone, the velocity color turns quickly to blue, indicating a sudden slowdown in airflow separating from the ankle surface. Let's now examine the scenario involving the two dials. The air experiences a slowdown as it encounters these frontal areas, leading to a rise in pressure. High pressure on the frontal area means drag, which constitutes the first negative effect of the dials. The airflow then gains velocity around the dials as it would around a standard cylindrical shaped object. Finally, the flow slows down and creates a large depression zone, which generates additional drag. The ankle, which seems to be out of the dial's influence area, shows the same abrupt change from red to blue, indicating flow separation. The same color image can be enhanced with LIC, showing the direction of the flow and the formation of vortices in the blue and green areas. Here is a representation of the shoe's vorticity, and you can clearly see the turbulence created by the two dials. Two final images featuring streamlines effectively illustrate the air motion around the dials and align with our previous considerations. And now some numbers. The first simulation yielded a drag force of 0.45 newtons, while the second simulation recorded a drag force of 0.40 newton. The addition of two dials to the shoe and ankle system resulted in a 0.05 newtons increase in drag force, a 12% difference between the two scenarios. Since the environment we studied can be considered exhaustive in terms of the dial's effect on the whole cyclist, we can generalize the impact of two shoes with two BOA dials each as an increase of 0.1 newton in the total drag force of a cyclist. Given that a cyclist riding at a speed of 50.4 kilometers per hour in an aerodynamic position, as the one in the image, generates a drag force of approximately 24 newtons, the impact of these four BOA dials is 0.41% of the total drag force. Thanks for listening. We hope you enjoyed our explanations, and if you have some questions, let us know. Bye.